Hello and welcome. Today we'll be talking about the next part of the momentum series, conservation of momentum. In order to understand this topic, we're going to go back to our two cars. Remember in our previous video, we only looked at the red car. We used the red car, we gave it an initial velocity of 10 meters per second, and then we saw how the red car changed its momentum. Okay? Some of you might have been thinking, what happens to the blue car then? Do we realize that the blue car also has a change in momentum from 0 to 10? So let's investigate this. So our red car had a mass of 1. It had a final velocity of 0. And it had an initial velocity of positive 10. Positive times negative gives me 10. And we said it had negative 10 kilogram meters per second. Okay, let's see what happens with the other car. The other car also had a value of 1. Okay, it finished with a positive 10 because it was going in that direction, which is the positive direction. But it initially had 0. And if I multiply that, it gives me 10 kilogram meters per second. What do you notice between these two answers? They are equal but opposite. Maybe it's a coincidence. Let's go and try with a few different values. So now I gave the blue trolley a 3 kilogram mass. Let's see if the mass would change the fact that they had the same change in momentum. Okay, so we saw that the red one came with 10. And after the collision, the red one rebounded with in the opposite direction with a negative 5. Why is it negative? Because he went in the opposite direction. The blue one started with 0, and now it had a positive velocity of 5 meters per second. So the red one still had a mass of 1. It had an initial velocity of positive 10. Positive times negative gives me negative. But it ended with a final velocity of negative 5. Okay, so here we see that the change in momentum is negative 15 kilogram meters per second. The blue one had a different mass. It had a mass of 3. It ended with a positive velocity of 5 minus an initial velocity of 0. Okay, and if we multiply that, we get a positive 15 kilogram meters per second. So what do we notice? We notice that, okay, the red change in momentum is equal but opposite to the blue change in momentum. Okay, or we can put the negative on this side. They are equal but opposite. Okay, what does that remind you of? Newton's third law, which said if an object A exerts a force on object B exerts an opposite but equal force. Now, because of Newton's third law, we see that the momentum in a system, these two cars form what we call a system, stays the same. Okay, the change in the momentum that the one undergoes is the same change in momentum that the other one undertakes, and therefore it's because the forces are equal but opposite. So the change in momentums are equal but opposite. So this brings us to the law of conservation of momentum. So if I add the total momentum, the momentum of the red and the blue car before, and I add the momentum of the red and blue car afterwards, the total momentum of my system initially will be equal to my total momentum finally. So let's go and test that out again. So the initial momentum of the red one plus the initial momentum of the blue one adds up to a value equal to the final momentum of the red one plus the final momentum of the blue one. Okay, and if we put our formula, momentum is mass times velocity. Now what I've done here is we use the symbol U for initial velocity we use the symbol V for final velocity. You can say VI, VI, VF, VF, but that also just makes the writing a bit more. So this is perfectly fine. So we know that the red one had a mass of 1 and a positive 10. The blue one had, in the last scenario, a mass of 3, but it was stationary, so it had a velocity of 0. Then the final velocity of the red one was negative 5, and the final velocity of the blue one, which had a mass of 3, was positive 5. So if this is true, if the total momentum before is equal to the total momentum after, the sum on the left hand side would be equal to the sum on the right hand side. Let's see if that works out. So here we get 10 plus 0 is equal to negative 5 plus 15. And we end up to see that 10 is equal to 10. Please note, it doesn't say the total momentum before is equal to the negative total momentum after. Okay, they are exactly equal. Okay, so don't confuse the fact that the change in momentums are opposite but equal with the fact that the total momentum before is equal to the total momentum after. Let's look at another example. In this example, we're going to try something else. We're going to try a inelastic collision. Now, what's going to happen here, instead of bouncing off, they're going to stick together and move together finally. So an elastic collision is if they bounce, an inelastic collision is if they get stuck with each other. So let's see what happens in this case. Okay, let's look again. Red one has an initial velocity, blue one is stationary, and when they bump into each other, they get stuck and they move together. Okay, so now we take the same formula, total momentum initially, the sum of the momentum before, must be equal to the sum of the momentum after. Okay, we have the masses and the initial velocities here, and then you would notice I color-coded this. What does that mean? Since they stick together, they have a common final velocity. And if I mathematically take that out, what am I going to be left with? I'm going to be left with the mass of the red one plus the mass of the blue one. Okay, so we'll put our equation in there. Why do I do this? Because they now move together. They've got a single final velocity. Okay, this is a shortcut, but I will show you guys if I don't do this and we just keep it that way. There is a reason why I want to do this, because later on we're going to use this to find that velocity. And it's always easier to find one unknown versus two. So if we want to find that velocity, we will take it this way. But for this sake, they both move together at a positive 2.5. So we know that that is a positive 2.5. We know that the mass of the red one was 1. That the mass of the blue one was 3. Okay, and on this side, we had 1 times 10. And we had 3 times 0. So let's see if the conservation still applies. If the left and the right equals the same thing, we get 10 plus 0 is 10. We get 4 times 2.5 is 10. And momentum has been conserved. So let's see if we can use this formula to predict the final velocity even before it happens. Let's play around with our velocity. So let's give this one a mass of 2, the red one, and the initial velocity of, let's say, 8. And now we can choose, should the blue one go towards or should it go away from? Let's make it go away from at a slower velocity. So it's like a minibus driving into a slow truck. And then because it's elastic, they will stick together. Okay, so they will have a common final velocity, and we want to predict what that final velocity would be. So in my equation now, I've placed the 2 times, the red one had a mass of 2 with a velocity of positive 8 because it was going to move to the right. The blue one has a mass of 3 with a positive velocity because it's also moving right. Then we're going to calculate what's going to be the final velocity, and we add the masses together. So this is 16 plus 6 gives us, if we add it together, 22. And that is 5v. Okay, 5 times v gives us 5v. So that means v is equal to 22 divided by 5. And if you substitute that into your calculator, you get 4.4 meters per second. So let's go and see whether the final velocity of the two is 4.4 meters per second. So if we press start here, we see they travel at 4.4 meters per second. So we have successfully predicted the final velocity. Okay, we could have also done the same thing, but we could have made it a collision. So they're driving and then they bounce back. This one travels slower, this one goes faster. So that's the difference between an elastic collision and an inelastic collision. The next one that we'll look at is an explosion. Now, an explosion is any two objects that are connected together and shoot away. So in most explosions that we will see, they both start at a 0 initial velocity. So if we make them explode, they are going to go in opposite directions, and then we will see what happens with their masses compared to their velocities. Let's give them equal masses for this one. Okay, so let's start. What do we notice? They have equal masses and equal but opposite velocities. Let's look at why that happens. So here we've got our equation. Total momentum before is equal to total momentum after. I substitute the mass in the initial velocities and the mass in the final velocities. What we notice is because both of them have 0 velocity initial, our total momentum beforehand must be 0. That means the sum of these two momentums should also be 0. And if I have negative 10 and positive 10, they cancel and they are also 0. So let's now look at another example of this. Let's change their masses. Let's make it 3 and 2. 2 for the red one, 3 for the blue one. And let's see if this still adds up to 0. Negative 5 and positive 3.3. So now if I substitute the values, sorry, I forgot the masses. 2 times 0 gives me 0. 3 times 0 gives me 0. So initially, because each one of them weren't moving individually, they both had 0 momentum. So if I add 0 plus 0, it gives me 0 momentum on this side. So if I say 2 times 5, that gives me negative 10. And if I say 3 times 3.3333, it only showed me 2 decimals, but it's 3 recurring. It would give me positive 10. And hey, negative 10 plus positive 10 gives me 0 on both sides. So with conservation of momentum, the conservation of momentum equation is not set in stone. The momentum P of all the objects in a system before is equal to the momentum of all those objects after. The scenario would determine how you break out the conservation of momentum equation. What do I mean with that? If they travel together, they have the same velocity. So if they travel together initially, we have the one V instead of two different V's. And if they travel together finally, we take out a V commonly. The formula that we use though is the following, where the sum of all the momentums before is equal to the sum of all the momentums after. And now you'll see very much more subscripts here because I'm not using color. Mass 1 times the velocity of mass 1 initially plus, so you could have said that with u1 plus mass 2 times u2 initially, u2 initially gives me mass 1 times v1 finally, and mass 2 times v2. Okay, so here's the equation if we use subscripts without color. Okay, and you're required to write down the equation. So let's look at a few examples. The principle of conservation of momentum says in any collision or explosion, momentum is conserved, provided that there are no external forces that have an effect. Okay, so here we see two cars racing. The one car is 1,000 kilograms and it drives at 50. The other car is 800 kilograms driving at 20, and they bump into each other and connect. What is the final velocity? So since they connect, we have one common final velocity. So we say the initial 50 times 1,000 plus 20 times 800 must be equal to the sum of their masses, 1,800, times the final velocity that we want. And if we solve that, we see that their final velocity is 36.7. Okay, so here, one more example. A 95 kilogram pitcher at rest throws a 0.1 kilogram baseball 40 meters per second to the right. How fast would the pitcher be going in after the throw of the ball on a frictionless surface? So imagine this happens on ice. So here we have the information that both the pitcher and the ball was initially stationary. So if we add that up, 95 times 0, 0.15 times 0 adds up to 0 on this side. Okay, so we treat this as if it's an explosion, similar to an explosion. Then we want to calculate what is the final velocity of the pitcher going to be if this happened on ice. And if we times 0.15 times 40, we get 6. Okay, so to calculate this, we are going to say that 95V is equal to -6. So therefore V will end up being -6 divided by 95, and that gives me 0.063 meters per second. So the guy is much heavier than the baseball. Okay, so he will only have a very small velocity to add up to -6. Okay, oh, and the velocity would obviously be negative because it's in the opposite direction. So he would have to have a velocity of -6, and because his mass is so big, his velocity needs to be very small to get a total of -6. So if I say -0.063 times 95, it's going to round off to -6, and the -6 and the +6 cancels. In the next example, we'll see how fast is an 85 kilogram receiver for American football traveling at 6 meters per second to the right. Going to go after catching a 0.43 kilogram football traveling at 30 meters per second to the right. So as he catches, they both move together, so they both have the same final velocity. So if we look at it, momentum before is equal to momentum after. They both have the same final momentum of velocity, so we take out the velocity initially. It's easier to calculate one unknown value than two. So we substitute our values. 85 times 6 plus 0.43 times 30 gives me the velocity that I want times the sum of their masses. So 85 times 6 gives me 510. 0.4 times 3 times 30 gives me 12.9. And if I add the masses together, I get 85.43. So that gives me 522.9 is equal to V times 85.43. So as I'm solving V, it's going to be 522.9 divided by the total mass, 85.43. But before I write the answer, this guy traveling at 6 meters per second catches a ball going in the same direction. The ball is much lighter than him, but it does increase his momentum. Okay, the ball and the guy, the ball's going to slow down, the guy's going to go slightly faster. So if we get this answer, we expect an answer bigger than 6, but not much bigger, and we get a value of 6.12 meters per second. So catching that ball made him go slightly faster. In the same way they use rockets, moving rockets, and then they shoot in space. The moment the fuel tanks are used up, they shoot the fuel tank backwards. And that detachment of the fuel tank in opposite directions makes the projectile or the thing going to the moon or wherever go faster, and the backboard going backwards. Okay, one nice thing that I didn't say about this equation is the following. We have mass on both sides, we have velocity on both sides. So if it's grams and grams, the units would cancel. If it's centimeters per second and centimeters per second, the units will cancel. Or if it's kilometers per hour and kilometers per hour, the units would cancel. So in this case, we don't have to stress about converting units unless only at the end if we need to convert this to meters per second. Okay, so conversion here is not such a big deal depending on the question what they want at the end. I hope that you are not too confused, and go and try this now, the multiple choice questions, and see whether you can do this concept. You're going to have to think a little bit about it. I hope you have an awesome day. Thank you and goodbye.